All right, so in this video, we're going to be deriving the D5h character table. And so the first thing that we do whenever we do any of these derivations is we figure out all the different symmetry elements that exist in this point group, and also how to group those different symmetry elements into classes. And so these DNA point groups are fairly easy point groups to visualize. They're going to have the same symmetry as any regular polyhedron with that same number of vertices. So for example, just a flat planar pentagon will have D5h symmetry, or so something like a cyclopentadienal ligand by itself, anion by itself would have that symmetry, or ferrocene, which is an iron atom coordinated to two cyclopentadienal ligands. That would also have D5h symmetry if the hydrogens on each of these ligands are eclipsed. Okay, so these two pentagons are stacked on top of one another and exactly overlaid. And so anytime we do this, we of course always have the identity operation. And so the identity operation we use the symbol E for, and the hat notation here represents that it is an operation. And then this point group also has a C5, that's the principal rotation axis. Okay. And for this, we're going to have, so that's a 72-degree rotation. Takes this hydrogen to this hydrogen, for example, this hydrogen to this hydrogen, spins them all 72 degrees, one slot along this pentagon. We can have a C5 twice, be 144 degrees. We can have a C5 3 times, and then a C5 4 times. We can't do a C5, we can't do a C5 5 times. That's equivalent to identity. All right, and then we also have in this molecule perpendicular C2s. And so any D point group, we always have N perpendicular C2s. So N is 5, so we're going to have 5 perpendicular C2s. We can call those C2, C2 prime, C2 double prime, C2 triple prime, and C2 quadruple prime if we want. And those are running perpendicular, right, as we just said. So it's going to run through the central atom, and we'll have a 180-degree rotation. A C2, right? That's what a C2 is. And what that does is it takes the two faces of the ferrocene molecule and interconverts them. So it would take this hydrogen and interconvert it to that hydrogen, for example, right? Spins it. And so the one that we drew here is going underneath these two atoms. And so that's fine, but then you'll also have ones that go through all the different atoms, so five different atoms, right? So you'd have one going through this, although through the center atom, it's harder for me to draw. It's easier for me to show you here on top, even though that's not where the C2s are. But it's what they bisect or going along, but they would all be going through the center atom. Okay, and we'd also have a sigma H, that's a horizontal mirror plane. And so it's horizontal, perpendicular to the principal rotation axis, this the C5 that we talked about. And you can see what that mirror plane does is the top face of the ferrocene molecule is looking at the bottom face of the ferrocene molecule on the mirror, in the mirror. So it's interconverting these hydrogens, right? And so we call that sigma H operation. And then we also have 5 different sigma V's. So vertical mirror planes. Again, we can call them with these primes in double prime notation. And just like these 5 C2s, perpendicular C2s that we talked about, they also cut through in the same sort of way, right? So you can see this one's cutting through that atom, but the other 4 cut through the other 4 carbons. And so this mirror plane would interconvert this hydrogen with this hydrogen, and this hydrogen with this hydrogen, for example. And then we can start thinking about how we can actually combine some of these things. And anytime you have a sigma h and a principal rotation axis, you can combine those and make an S5, right? So an S5 is equal to a C5 followed by a sigma h is an improper rotation axis. So we have that. We can also do an S5 twice. If we do that, it will be a C5 twice. Followed by a sigma h twice. Well, sigma h twice takes top to bottom and then bottom to top, so that does nothing. So that's just equal to C5 twice. So that's not a unique operation. But we can do an S5 three times. That'd be equal to C5 three times, followed by sigma h three times, which is equal to C5 three times, followed by sigma h. But I have an odd number of flips, so that goes top to bottom, bottom to top, and top to bottom. So now we went top to bottom. So that's a unique operation. So our unique operations for improper rotation axes are S5, S5 three times, S5 four times we can try. That's going to be a C5 four times followed by an even number of flips. Top to bottom, bottom to top, top to bottom, bottom to top. And that we just did top to top, even number of flips on the mirror planes there. So that's not a unique operation. We've got C5 four times. We can do S5 five times. That's going to be a C5 five times followed by sigma h five times. Well, C5 five times is equal to identity. Sigma h five times is the odd number of flips. That's equal to sigma h. We can then do S5 six times. That's going to be equal to a C5 six times followed by sigma h six times. Sigma h six times is identity. C5 six times, well, that's a what is that? A 435 degree rotation. Basically, 72 degree, 432 degree rotation. 72 degrees more than 360 degrees, which is just equal to 72 degree rotation, which is C5. We have sigma h six times, which was identity. So we already have C5. That's not a unique operation. That's up here. What about S5 seven times? S5 seven times is C5 seven times followed by sigma h seven times. C5 seven times is the same as a C5 seven minus 5, right? C5 five times is identity, so it's a C5 twice, followed by sigma h because we have an even number of flips, and that's unique. And then an S5 eight times is equal to a C5 eight times followed by sigma h eight times. Sigma h eight times is equal to identity. C5 eight times is equal to C5 three times. And sigma h is an even number of flips, that's equal to identity. So we just got C5 three, not a unique operation. C5 nine times, we got the S5 nine times is C5 nine times followed by sigma h nine times. That's equal to a C5 four times followed by sigma h. All right, that is a unique operation. And then S5 10 times is equal to a C5 10 times followed by sigma h 10 times. That is equal to identity. Even number of flips, 720, we're doing Tony Hawk moves here, 720 degree rotation, which just gets you back where you started, so that equals identity. So we already have identity. So the unique ones here are, well, S5 is what we started with, okay? That was unique, see, because the S5 was C5 followed by sigma h. It transforms atoms differently than any of these other operations. At S5 three times, that was unique. It's kind of related, right? It's C5 three times followed by sigma h. And I'm actually going to use a different color here for that one. Let's use green. We'll see why in a second. And then we have S5 seven times was also unique because that was a C5 twice followed by sigma h. And then going back to blue here, we had an S5 nine times, which is equal to C5 four times followed by sigma h. So we have these four different types of improper rotations that are unique. I'm going to list them here. S5 three times, S5 seven times, and S5 nine times. And these are actually all the different symmetry operations that we have in this point group we have 20 different symmetry operations here. Now we get to group them into classes. So I'm going to do that in red here above here. And I'm going to drop the hat notation. So identity operations always in a class by itself. There's nothing else like it. These C5s, we have 4 different C5s. And the ones that I'm boxing here, C5 and C5 4 times, those are going to go into the same class. We're going to call that class 2C5, again, dropping the hat notation, 2 because we have 2 operations. Now, why do we put those together? We put those together because when we do a C5, if we define it in this direction, takes these hydrogen atoms and put it there. And a C5 4 times takes the hydrogen atom and goes all the way to here. But if we just defined the C5 as going in the other direction, it would be the same as doing a C5 4 times. So therefore, mathematically, these are very similar, and there's an axis system. You can determine how you draw the axis systems, you will get C5 and C5 4 times being mathematically equivalent. And you need some symmetry operation to interconvert those axis systems that make it equivalent elsewhere in your point group. And these sigma v's end up doing that for you, okay? Very similar story. So we put these C5 and C5 4 because they're mathematically similar into the same class. Very same story with the C5 twice and the C5 3 times. Those are going to go into their own class. I'll use a different color here. So these two go together in a class we'll call the 2C5 2 class. The reason why is both these operate similarly, depending on the axis system we get going. C5 twice goes that way, or C5 3 times goes that hydrogen, that hydrogen. But if you define your axis systems in the opposite way, we would go the other direction, and a C5 2 times would be the same, do the same thing in terms of how it moves the atoms as a C5 twice. So C5 3 times, C5 twice, therefore, are very similar mathematically, and they go in the same class. We call that class 2C52 because they both work like C52s. They both work like 144-degree rotations, depending on how you define your axis systems. And there's 2 operations in that class, the C52 and the C53. Okay, what else do we have? We have all of these C2s. They're all perpendicular C2s. And so all those are mathematically similar. They go in their own class, the 5C2 class. We have a sigma H that goes in a class by itself. We have 5 sigma V's. Those are mathematically similar. Those go in a class. And then we have 4 improper rotation axes. And these ones, again, we're going to have to break up similarly to how we broke up the proper rotation axes, the C5s. We have the S5 and the S5-9, and those are going to go together into a class we'll call the 2S5. And the same thing as the logic before. S5-9 is C5-4 followed by sigma H, and S5 is C5 followed by sigma H. So we have C5 and C5-4, just like C5 and C5-4 before went in the same class. Here, very similar, they should go in the same class. And then we have, lastly, the S5-3 and the S5-7 times. Those go in another class called the 2S5-3 class. When we decompose those, we see that C5-3 followed by sigma H and C5-2 followed by sigma H. And again, the C5-2 and the C5-3 and the sigma H went in the same class for reasons we discussed before. So there you have it. Those are the 20 symmetry operations of the D5H point group. And they get grouped into 8 different classes that we showed right here. And so what we're going to do in the next video is use these different classes that we've come up with, these 8 different classes, to figure out the 8 irreducible representations of the character table and figure out what those values are. And that's how we'll figure out, all the characters for the character table.